All right, so thanks for popping in here to learn about some gas laws. Today we're going to show you a couple of gas laws that are important for you to know, not only from their equation, but that the fact that we can manipulate them to find what it is that the problem is asking for, or what it is that we'd like to find, the variable. So a couple of things that we first need to know are, what are the gas laws? Gas laws that you need to know, and the most known would be Boyle's, Charles. Okay. And we can go so far as to list a couple of other ones. Let's see. And the reason that I'm going to put this guy on here is because it's nice to know how he's contributed. Okay. We need to talk about Avogadro's law. And then we're going to talk about, either you'll hear it as the combined or ideal. And I'm going to actually highlight this one for us, okay? Because this one is actually going to be the one that you'll remember. And aside from Charles and Boyle's, this is the one that you're going to want to remember the most, okay? And that most of the time we'll be using, okay? But there will be some application here and here. This is just a concept, but you'll be using these three the most. Okay, so let's begin. Boyle's law. Boyle's law is basically talking about two things: volume and pressure. Very important to know. So if you were asked a question that was conceptually written and it talked about what relationship did Boyle's law show, you'd need to know that it's volume and pressure. Specifically speaking, it's volume times the pressure. Okay? And the reason that that's important is because when we need to manipulate this equation to find out, say we were given two sets of pressures in one volume and we wanted to find the second volume, you need to know in what ways we can manipulate the equation. Okay? So for this, okay, we need to remember the following equation. P1 V1 equals P2 V2. Okay? So the statement that Boyle's law says is that the volume of a given mass of any gas is going to be inversely related to the pressure when the temperature is constant. So as you note, there is no temperature here. So I'm going to put on this side that temperature is constant. Okay, and so what you need to know is that when the volume of is inversely related to pressure. Okay, which makes sense, right? So let's say, hypothetically speaking, I was given a volume, an initial volume, so V1, an initial pressure, so P1, and then I was given a final volume, okay, or a final pressure, we shall say. I'm starting to look for V2. What we'll do is we'll divide this by P2. And so what we're saying by inverse is to kind of undo and eliminate and isolate any of these variables to solve for the missing one, we're going to have to divide, because this whole process here, this equation, is all based on multiplication. Okay, so to undo things, to undo / change and isolate a variable, we need to divide. Okay? And that's the same as saying something is inversely proportionate. It's usually going to be in a fraction form, so we will be dividing. Okay? So this right here, P1V1 over P equals P2V2, is one of the equations that you will be familiar with when it comes to gas laws. Okay? And this is Boyle's law. Okay? The second is going to be Charles' law. What Charles' law does is he's talking about volume, right? So the given mass, right, is when we're trying to say that when there is a given mass for some ideal gas at a constant pressure, the volume is directly proportionate to its absolute temperature. Okay, so what is constant in this? We're going to say that pressure is constant. Okay, whereas before we said that temperature is constant, here pressure is constant. Okay, and so then what we're going to be relating is we're going to be relating volume over temperature. So volume by temperature, or volume divided by temperature. Okay, so for his equation, you're going to have V1 over T1 is equal to V2 over T2. Okay, so this is a very important equation, and this is one that we'll need to be making sure that we use as well. Okay, the difference being that here we're going to multiply to undo. Okay, the previous one we are dividing to undo. Okay, so they're just a little bit opposite, and it's something that we just need to be able to recognize. Okay, but okay. So anytime that you want to find a variable that's desired, you're going to have to multiply to isolate it. Okay. All right. And again, the key thing here is this is going to be talking about, and the relationship is volume by temperature. Charles is volume by temperature. Boyle's is volume and pressure. Okay. There's always going to be a constant in these. So you just need to make sure either remember what the constant is, or more importantly, know the relationship. I recommend that you know the relationship. Okay. It makes things a lot easier. Now, the other relationship that we were talking about that I kind of just want to touch briefly on is Gay-Lussac's. Okay. And I'm just going to touch base, just quickly do this one. The thing about him is that what we're comparing here is that we have a constant volume. Okay. So here, the volume is constant. Okay, so what are we relating? We're relating pressure by temperature, or pressure over temperature. Okay, so these are the things that you just have to remember. And if you notice, every single one of them invented something, and they're all very similar, just testing for different things. Okay, so it's kind of helpful, right? Let's write here, this is what's constant. It's nice to know that. Okay, and then go ahead, and here is the equation. It's very similar to Charles's law, where we're just going to have P1 over V1, or T1, I'm sorry, P2 over T2. Okay. Again, you're going to multiply to get what's desired. Okay. These are very similar. All right. As far as Avogadro's law goes, all we need to know and what you'll remember is 6.022 times 10 to the 23rd. Okay, so Avogadro's law helps us when we're dealing with molar volumes, okay? And so when you're trying to understand how something is related, what we're saying here is that any volume occupied by an ideal gas is going to be proportionate to the number of molecules of that gas present in a container. So what is it relating? It's relating volume by the number of moles, okay, or number of molecules, okay? So you can say this, but I'm also going to put moles here because sometimes it's easier for students to connect those dots when we actually say moles. Okay, but remember Avogadro's law can be any sort of unit. In this case, I just like to talk about it as moles. So this is the relationship. And if you say by, remember by is indicative that we're dividing. So it's going to be the same as volume V1 over N1 equals V2 over N2. Okay, and actually I'm just going to say volume over moles. Okay, so and again, it's V1 over N1 equals V2 over N2. And just being the number of moles, molecules, whatever the question may be asking. Okay, and now we have the most important, which is our combined gas law. Okay, I'm going to make this huge here because this is literally the most important one. What this gas law does is it literally takes Boyle, Charles, and guys, all of them in together, including Avogadro's law, and it talks and it helps us figure out and relate everything together. Okay, now we're going to introduce to you one more thing. So we have, this is the equation, PV equals nRT. Okay, so this is the equation that is the ideal gas law. PIV nert. So if you hear me refer to it as PIV nert, that's why. Okay, because that's what, if you look at it, PV, PIV, and then nRT, nert. All right, so this is PIV nert. So what we're relating is pressure is P, volume, V, moles, I can also say molecules, right, which is N. Then we have something called the universal gas constant, which is R. And then we're going to have temperature, which is K. Okay. A few things that you need to know. Always, always, always temperature needs to be in Kelvin. It will be presented to you in a problem that has Celsius and you need to convert it. Remember, it's just adding 273. As far as the universal gas constant goes, you will be provided this on our exams. However, you should know that it's 8.314, okay? And then you can say kPa times liters over moles Kelvin. Okay, the units here is not really important. All we need to know is that is, since the universal gas law, it's going to combine all of the different types of units, and just that's what it is. Okay, because it allows us for us to cancel things out, and then when we're doing dimensional analysis, we can use this as a conversion to get us from one place to another. Okay, because it has all of the units together. So don't be scared by the units. But this is something that we will need to remember, this value, And so I highly, highly recommend that you start remembering it. Okay, it makes it easier. All right, so now when we're dealing with this, the way that this is how like I said, this is how we will write it originally. They write it as PV equals nRT, but I want to let you know that you could also write it a couple of other ways, right? So let's say we have PV equals nRT, and we're trying to solve it for, actually, let's write this down here. Okay, manipulate, call it the manipulate. Okay, so here's the original. And now let's say we want to solve it, we want to isolate n. Okay, so now our goal is we're going to isolate n. We don't know n, but we know everything else. And I'm going to show you how to do that. Okay, so what we'll do is you'll start with PV equals nRT. And then we're going to go ahead and divide by RT. And that will cancel those things out. So now you'll have n equals PV over RT. Okay? Now let's say we want to isolate R. So PV equals nRT. You can divide by nNT. Okay? And those would cancel out. So then we would have PV over NT equals R. Okay, so the same rules apply, right? Just know that what you're multiplying, and when you're multiplying to undo, you divide, and et cetera, et cetera. But what we're saying here is that this equation can really be isolated for many different things. Now, would we ever want to isolate R? No, because isolating R is a constant, and we were already always knowing the constant. So we don't need to ever isolate R, right? Do we have to isolate N? Maybe, okay? But you're really going to be focusing on how to manipulate this equation for anything like the pressure, the volume, or the temperature, or the number of moles. You'll never really have to isolate for R. I just wanted to show you that you could do that if you'd like, okay? But in theory, that's just different ways to manipulate, okay? You'll always know this constant, so you're never going to have to find it, but again, just an example. Okay, so now what we're going to do really quickly is we're going to do an actual example with some math behind it. So the first thing that we're going to do is we're going to use this example. So example 1. Let's say we have lungs of a normal adult, and they hold 5.0 liters, okay, of air. Okay. We also know that this only takes place under normal, or typical, I should say, atmospheric pressure. Okay, which is 760 millimeters of mercury. Alrighty. So that's under typical. If we have a diver now, this adult wants to dive, and she dives, and then her lungs compress to 4. Okay, so now we're going to say she's diving. She dives, and now her lungs are compressed to 4.0 liters of air. Okay, we want to know what is the pressure surrounding her. Okay, so this is what we're trying to solve here. What is the pressure? Key thing here is the pressure. So if I were you, the first thing that I would do is list my knowns. Okay, so what we know. So we are given a 5.0 liters of air. Okay, so we know that that's liters. I'm going to say that that right now is going to be considered a volume. Okay, so we know a V1, and we know that we're going to have a second volume of some stature because I see a 4.0, so that would be a V2. Okay, so we're given two sets of volume, one at 5.0 liters and the others at 4.0 liters. Okay, now I'm given a 760 millimeters of mercury because that is typical atmospheric pressure. And not to mention, the question is asking what pressure is surrounding this diver. Okay, so that's going to say, well, our initial pressure, P1, was 760 millimeters of mercury. Okay, so here's the thing. You can leave this as 760 millimeters of mercury. You don't need to move it to atmospheres, okay? As long as your volumes are in the same exact unit, there's really no converting here. So if we think back about all of the laws that we just learned, what and who combines or shows a relationship between volume and pressure? Volume and pressure, volume by temperature, pressure by temperature. Okay, so we know for a fact now that we're going to be dealing with Boyle's law. Okay, so Boyle's law, which talks about P1 V1 equals P2 V2. Now, I don't know the new pressure, the second pressure. That is the unknown. I don't know the second pressure. So I have to first isolate P2. So to do that, I'm going to take this and I'm going to divide by V2. Okay? So now my second new equation is going to be P1 V1 equals P2, and then this is all going to be over V2. Okay? So now you can go ahead and solve it. So our first initial pressure was 760 millimeters of mercury. And then our first volume was 5.0 liters. And then the second volume was 4 liters. So then we're going to do like this. And then we're going to say that that's equal to the second pressure. And so multiply first, then divide. Hint, hint, hint. So multiply first, divide second. Okay, so always do that first. And so then we should get an answer of 950 millimeters of mercury equals P2. Okay. So that's how we would solve something like that. Let's do another one. Okay. Okay. Let's see. Okay. Okay. So now let's say we have a gas is collected. So 2. A gas is collected, and it's found to fill 4.73 liters at 35 degrees Celsius. What will the volume at standard temperature be? Okay, so the first thing is these questions are the best and most favored by instructors because you're given the standard temperature. And when students first start going in and dissecting this the same way that we just did that last problem, they're going to think, okay, 4.73 liters. I'm going to circle it. That's a volume. Here is a temperature. So let's start V1 and then that's a T1. The T1 is 35 degrees Celsius, but Liz said always, always, always transfer it to Kelvin. And then the first volume again was 4.73 liters. Okay, so that's going to be 308 Kelvin. Okay, and then I have, what will the volume be? Well, we're looking for V2, and then, well, what's T2? What's T2? This is why it's a very tricky question. And standard temperature, remind you, is going to be like what we're used to. So 25 degrees Celsius or 273 Kelvin. So that's standard. So 273 Kelvin is standard. Okay. So now all you have to do is determine, okay, well, who's relating volume and temperature? Well, this is Charles's law. Okay, so we know that it's going to be V1 over T1 is equal to V2 over T2. We're trying to find V2, so let's isolate V2 by taking T2 and multiplying it. So our new equation is going to be T2 V1 over T1 is equal to V2. Again, always do your multiplication first and plug things in. So we'll have T2 is 308 Kelvin by 4.73 liters all over, I'm sorry, this is 273. Good catch. By, this is going to be 308 Kelvin. Okay. Oh, wait. Yeah. Okay. So you're going to take the 273 Kelvin because that's the standard, multiply that by the 4.7 liters, and then you're going to divide by the 308 Kelvin. And so what you'll have is what temperature? I'll let you figure that out. Okay. The second is we're going to go and try and figure out, let's say we have 9 liters, 9.0 liters of gas, and this is going to exert 83.0 kilopascals. Okay, and then this is going to take place at 35 degrees Celsius. We want to know what would the required temperature in Celsius be to change the pressure to standard pressure. So what would the required temperature in Celsius, okay, be to change the pressure to standard pressure? Okay, so the first thing that we're going to do is you need to change the 35 degrees Celsius to Kelvin. So we know that 35 degrees Celsius is 308 Kelvin. Okay, so we're given a volume, which is 9.0 liters, and then we're given a pressure, 83.0 kPa, and then we're given a temperature, okay. So now you think, well, do we really need the volume? Okay, do we need the volume? No, we don't need this. This is not necessary, okay? It's a trickery. So when you start listing things out, make sure that you're well aware of what you need and what you don't need, because the question is stating what would the required temperature be. So what are we trying to find out? We're trying to find out T2, okay? And then pressure, P2, is standard pressure. And standard pressure is what? Okay. The standard pressure in the kilopascal, what that is it's 101.32 kPa. That is standard pressure. That's a volume. That's what the standard pressure is in kilopascals. Okay. Again, you would be given that on your cheat sheet for this class. So now you just go ahead and set this up. Here, we're going to be using his law. And so what we're relating is we're relating pressure and temperature. Okay, so in this case, P1 over T1 is equal to P2 over T2. We're trying to find T2, so we're going to multiply by T2. And so then we get T2 times P1 over T1 is equal to P2, or T2. We're trying to find T2, right? Why do I see? This is why you always have to pay attention to your math and not rush things. So let's start that again. P1 over T1 is equal to P2 over T2. And we're trying to find P2. So let's go ahead and multiply by T2. Oh, I was right. No, we're trying to find T2. Okay, so in this case, since we're trying to find T2, the first step is that we're going to basically do a couple rearranging. If you multiplied by T2 on each side, then you would get T2 times P1 over T1 is equal to P2. Okay, but that won't work, right? So then what can we do instead? Remember that they're inversely proportionate. Okay, so the thing that we have to do here is how can we get rid of this? And this is the same as saying times 1 over T2. Okay, so if we separate those out, then the new equation would be P1 over T1 is equal to P2 over 1 times 1 over T2. So 1/2 of that, right? 1 over that, whatever that value is. So then what we can say is, okay, well now I can take this, and since we're multiplying, I'm going to go ahead and divide by P2, because P2 over 1 is still P2, so if we divide this all by P2. Okay, and because we're dividing everything by P2, it turns into being P1 over T1 times P2 equals 1 over T2. And then you can go ahead and plug things in, all of those values. So let me just show you again how I got that. When you have a P2 over 1, anything over 1 is itself. And then we still have this times 1 over T2. Because we're multiplying, remember, we have to divide. So if I took this and I divided by P2, then that's over here. And now we have a fraction divided by a fraction. Well, to get rid of this situation, all you have to do is the opposite, which is multiplication. So we're going to take T1 times P2 and then keep that over 1 over T2. Okay, equals 1 over T2. So then we'll go ahead and plug it in. So our P1 was 83.0 kPa over our T1, which was 308 Kelvin, times our second pressure, which is 101.32 kPa. And that's going to be equal to 1 over T2. Okay. And so how do we figure out that 1 over T2? How do you get rid of that? Okay, if you to do that, you could just figure out the rest. It's the inverse. Okay, so after those three things, that should kind of guide you. Your ideal gas law is the same exact kind of idea when you're solving. So then what you could use then is you would just be given a bunch of different things. You could be given the liters. So let's say we're given a 3-liter gas and it was collected at 35 degrees Celsius and that the pressure was 705 millimeters of mercury. Okay, we want to know the volume at STP, which is standard pressure. So what is the volume at standard pressure? Okay, so the first thing that you'd have to do is find values. You need to figure out a certain value for the problem, okay? So let's say we were given, let's see. Even though here we're using the ideal gas law, PV equals nRT, you would say, let's change this to, oh, and let's also tell you, just give you a weight. We'll say 3.1134 grams, okay? So now it could actually rather say how many moles. Let's do it this way instead, right? So we'll go ahead and plug things in. You'll have 3.00 liters times, well, what's the volume, right? Which is 3.0. What's the pressure? The pressure is the 705 atmospheres, millimeters of mercury. Okay, the thing here is with the ideal gas law, two things. One, your millimeters of mercury must be converted to atmospheres. Okay, so what you'll do is you'll say, well, 760 millimeters of mercury is equal to 1 atmosphere. So if we had 705 millimeters of mercury, then what you're going to do is you're going to divide that by the 1 atmosphere. So you have to convert first. So we'll take this and we'll say 750.0 millimeters of mercury, and we're going to divide that by 760 millimeters of mercury, and that's going to give me an atmospheric pressure. Okay, so that's the first thing you have to do. And so from there, you'll get 0.9737 atmospheres. Okay, and again, you'll have to know what R is, always going to be 8.314. Okay, so if we continue to figure that out, this is our P, this is our P, this is our V, equals, we don't know N, then our R is going to be 8.314, and then the T, we had 35 degrees Celsius, we're going to multiply that by, we're going to add 273, so it should be 308. All right, and then you can go from there. And we'll figure out how many moles. I'm just pulling up a calculator. Just double check my math. Okay, so this is going to be the R, and this is going to be your T. So always have to have millimeters of mercury. It has to be in atmospheres. That's the first thing. And then the second thing is your Celsius needs to be into Kelvin. Okay, so you need to make sure that you have both of those units in here. This is the only one where the units need to be in that way. Okay, the other problems that we experience, as long as they all match, you're fine. But for the ideal gas law, you have to be in atmospheres and you have to be in Kelvin. Okay, so if you see any Celsius, please convert. If you see millimeters of mercury, please convert. Okay, so then here, I would multiply these first. Okay, you'll get a total. Then you can go ahead and divide by those. Multiply those first, then go ahead and divide. Okay, please, please, please always multiply first. Okay, it's easier, you won't have error, and it's just more efficient to do that way. Okay, so remember to convert. Okay. And then again, conceptually speaking, please make sure that you're aware of what each of those laws are relating. And that's pretty much the most important parts of the ideal gas law, Charles law, Boyle's law, and every other law in between there. And if you have any questions, feel free to reach out.